Swayam Prabha. Digital India. Educated India.
In this lecture and for the remaining part of this course, we will discuss some issues related to development of nonlinear finite element models. So, we will begin in today's lecture a brief introduction of what are the main issues, and we will start reviewing principles of continuum mechanics as much as is needed for purpose of illustrating the model development. So, first we can ask ourselves the question, what are nonlinear systems. So, a simple answer would be to begin by defining what is linear system, and a negation of that definition would tell us what is nonlinear system. So, if you have a system with input x1 producing output y1 and x2 of t producing output y2 of t, if we were to apply x1 and x2 together, the response would be sum of y1 and y2, and this is known as additivity property. Similarly, if we apply an input which is a scalar multiple a of x1 of t, the response will be a of y1 of t. So, if these two properties are satisfied, we say that the system is linear. A nonlinear system is a system that is not linear. So, one of these conditions would not be satisfied. So, this is a non-specific description. It does not tell you what exactly is the nature of nonlinearity, it simply tells that linear property is not obeyed. Now, some simple examples. Suppose if we consider a system whose input is x and output is y, and they are related through this equation y equal to mx plus c, is a scalar equation. So, if x1 is the input, let y1 be the output. Now, if I multiply the input by a factor a, we see that this is not equal to the principle of superposition is not valid here. Suppose y1 is response to ax1, and if we consider the response ay, which is not equal to y1. So, the system is not linear since it does not obey the scaling property. So, a lesson from this is that 0 input produces 0 output in a linear system. So, this is not satisfied in this case. Now, to fix the idea, we can consider a simple a single degree linear vibrating system with input x of t and output y of t. So, let us assume that system starts from rest. Suppose y1 is a response to x1 and y2 is a response to x2. If we now add these two equations, we will see that the output gets added up x1 plus x2. So, by inspection we see that y1 plus y2 is a solution of this equation, therefore, principle of first condition is satisfied. Similarly, if I multiply this equation input by a, we can again by inspection we see that a y1 is a solution. So, this system is linear. Now, if you now include a cubic nonlinear term alpha y cube, let under x1 let y1 be the response and under x2 let y2 be the response. Let us assume for the purpose of illustration that we have 0 initial conditions. Now, again as before, if I add the inputs, add these two equations, I see that I get this equation, whereas if I now apply an excitation x2 plus x3, that is x1 plus x2, if our response is denoted by y3, we see that y3 is not equal to y1 plus y2, therefore, system is nonlinear. Now, we can as an exercise you can examine the two examples, that is a single degree linear system and single degree nonlinear system, by including the effect of non-zero initial conditions. So, you can see what happens. Another system, x of t is the input and y of t is the output. So, if I now supply an input which is a scalar multiple of x of t, say a of x of t, we see that y1 of t will be a of y of t. That means scaling property is satisfied, but additivity property is not satisfied. Therefore, this system is still nonlinear, it is not linear, although one of the property is satisfied. Now, we can start discussing about what is the implication of system being nonlinear on response analysis. So, response to all the relevant loads need to be analyzed simultaneously. So, you cannot analyze response to individual loads and superpose the response, because principle of superposition is not valid. Now, I will illustrate with some simple cases, but I will just enunciate some of the properties. In undamped free vibration, frequency of oscillations depend on initial conditions, which is again an unusual feature if you are thinking this property for linear systems. Then harmonic inputs at frequency omega can produce harmonic responses at frequencies not equal to omega. It can produce non-harmonic responses, and it can also produce aperiodic responses. So, we can think of primary, subharmonic and superharmonic resonances, whereas in a linear single degree freedom system there is one natural frequency and one resonant frequency, whereas for a single degree freedom nonlinear system under a single frequency excitation there can be several resonances. Then reciprocity relations, which are one of the major features of linear system, are not valid for nonlinear systems. So, this property helps us to verify in a laboratory, for example, if a system is behaving linearly or not. Then, so large responses can occur at frequencies other than the driving frequency. This again refers to the subharmonic and superharmonic resonances that I mentioned. Then steady state responses depend on initial conditions, whereas in a linear systems under harmonic excitations, steady state when they exist they are independent of initial conditions, whereas this is not true here. Then there can be multiplicity of steady state solutions for nonlinear system. If you simply consider an algebraic quadratic equation ax square plus bx plus c equal to 0, even for such simple algebraic equation we already know there are two solutions. So, if it is a differential equation with nonlinear terms, one can still expect that there will be multiplicity of solutions. That indeed happens. Then system can possess multiple equilibrium states and display a wide range of bifurcations. This we have discussed when we talked about stability problems. Then concept of normal modes, natural frequencies and natural coordinates are no longer applicable for nonlinear systems. So, you cannot uncouple the equations of motion through a transformation. Then band limited excitation can produce responses with frequency content outside the bandwidth of excitation. So, this again is a very important aspect of nonlinear system behavior, both in response analysis as well as in experimental work. So, in fact, a narrow band, for example, a single frequency harmonic excitation can produce a very broad band response, and that type of behavior is known as chaos. We will not be touching upon that, I am just mentioning for sake of completeness. Now, some simple analytical solutions to illustrate some of the features. This is not an exhaustive coverage, but just to motivate you to special features that you should expect when you are dealing with nonlinear problems. Suppose we consider an undamped single degree freedom system with cubic nonlinear terms, and it starts with an initial condition A, x of 0 is A and initial velocity is 0. Mu is a parameter. If mu is 0, system is linear. So, we can see that solution is A cos omega n t, where omega n is this frequency. Now, if mu is not 0, one can expect that the frequency of oscillation and the nature of oscillations would change. It need not be at omega n, it will be influenced by mu. So, what I will do is I will represent the solution in a series x naught of t plus mu x1 plus mu square x2 plus so on and so forth. Then omega square, which is the frequency of oscillation, I will again expand in a similar series. Now, the unknowns here are x naught and omega n are known, x1, x2, alpha 1, alpha 2 they are not known. What we do is we substitute this assumed solution into this form into the given equation, and then collect terms on both sides which are powers of mu. So, if you collect terms on mu to the power of 0, I get this equation, mu to the power of 1, I get this equation. Now, if we can examine these solution to these equations. So, if we consider the first equation, it is x naught double dot plus omega square x naught equal to 0, from which we get x naught of t is A cos omega t. Now, x1, the equation for x1 has x naught of t on the right hand side, or here it is present here. So, if we now take that into account and solve the next level of equation, which is again linear, all these equations for x naught, x1 etc. will be linear, but solution at the previous step drives the solution at the next step. So, if we solve this problem, we get x1 of t to be given by something like this. Now, if that means I have expanded cos cube omega t, I am writing the right hand side. Now, if we examine this equation, if this omega and this omega are the same. So, as time becomes large, the solutions will become unbounded because we are in a resonant kind of situation, but system is undamped, it is conservative, therefore, this type of solutions are not possible. So, we demand that this multiplicating term alpha 1 minus 3/4 a square must be 0 for simulating the expected qualitative behavior of the system. So, we get alpha 1 to be 3/4 of a square. So, from based on this I can construct this solution, and using the initial conditions I will be able to write this solution for x1 of t. So, if we restrict our solution analysis to only the first two terms, I get x of t as a cos omega t plus mu a cube by 32 omega square, this cos 3 omega t minus cos omega t. Omega curiously is given by this. This omega depends on a. What is a? A is the initial condition. So, this is what I was telling, the frequency of free vibration can depend on initial conditions, and the response here is periodic, but it is not harmonic. Okay. So, period depends on initial condition. If mu is greater than 0, omega will be greater than omega naught, we call that hardening behavior, and mu is less than 0 we call softening behavior. Now, we can of course include higher order terms and do this. The objective of this discussion is not to illustrate the solution method, but to highlight the qualitative feature of the response. Now, a similar system under harmonic excitation, it is damped nonlinear system under harmonic excitation. If mu is 0, we know that response is harmonic for large times, that is a harmonic steady state. Now, we want to examine what should be the solution. So, if mu is 0, I have x naught of t is a cos omega t. Now, I will assume that for some a and omega, this could for some a this could be the solution. So, I will substitute this assumed solution into the equation of motion. This is only solution in the steady state. So, I will collect terms containing sine cosine terms, do a what is known as harmonic balance, and I get a pair of equations which are given by this. Now, this resulting equation is the frequency response function of the system. So, this is a forcing function f, amplitude, omega n is a natural frequency, omega is a driving frequency, a is the amplitude of response. In linear systems, this on the right hand side we will not get this a cube term. Okay. So, now if I plot this frequency response function, we start getting curves like this. In a linear system, we know that typically this curve will look like this. Now, in a nonlinear system, things change. In certain bandwidth of excitation frequencies, there are 3 possible routes, and which one is actually realized in a solution depends on initial conditions, and all 3 solutions need not be stable. Okay. So, now the question is, we have to examine stability of these multiple steady state solutions, and only those solutions which are stable will be realized. Now, if you were to do a thought experiment where you are increasing the driving frequency and you are starting with initial conditions which are on this branch. So, as you progress along this line, when you come here, the response suddenly drops. This is steady state response. This you will not see in the time history of response. It is 2 different time histories, but with initial conditions in the neighborhood of this response. So, it drops and it will follow this path. So, this branch will not be realized in such a calculation. But on the other hand, if you start with this side of the solution and you progress this way, keeping initial conditions in the neighborhood of the steady state solutions here, then you will see that you will move along this path and there will be an upward jump and it will be like this. So, if you ignore presence of nonlinearity, you may think that this is the resonant amplitude frequency, whereas it will be this, and that can lead to conservative estimate of the response. Now, how do we see in the regions where there are multiple solutions or even elsewhere, how do you know that these solutions are realizable? So, what we can do, we did this stability analysis earlier. What we will do is we will perturb the assumed solution by a small perturbation, substitute back into this, and we get now a time varying system where the assumed periodic solution appears as a coefficient. So, for a given value of A from this graph, for a given pair of values of omega and A, you come here and do a flow case analysis and find out whether the perturbations grows in time or not. So, that establishes whether the assumed solution is stable or not. So, if there are multiple steady state solutions possible, then which one will be realized is a question that you have to answer, and in fact it turns out that in regions where there are multiple steady state solutions, the responses will be dependent on initial conditions. So, this again is a newer feature. Now, there is another way of looking at this problem. I will quickly run through this. We again consider a similar system, a system with cubic nonlinearity, and I will seek the solution in the neighborhood of capital omega being in the neighborhood of omega naught. So, what we do is I perturb omega naught by a small parameter known as detuning. Okay, this is called as detuning. Epsilon is a small parameter. Now, I will arrange the amplitude of excitations and damping in this manner, and this method is known as method of multiple scales. The discussion on this is not focused on how to implement the method, but what the method tells us if you do it. So, I will skip this the details of this implementation of this solution, but what I will show is in this method I get solution in the form A of t cos omega naught t plus beta of t, where A and B are slowly varying functions of time which are governed by these two differential equations A and beta. Okay. Now, I can rewrite this equation in this form, and if a steady state exists, you can see that A and beta should become constants. So, in which case A prime and B prime must be equal to 0. So, the condition for steady state is that these are 0, these are nothing but fixed points of these two differential equations. So, corresponding to each fixed point of the equation for amplitude and phase, there is one steady state possible, and this again turns out to be multiple valued. And how do we study stability here? What we do is we study the stability of the fixed points, that also we have discussed earlier. So, in these two approaches, in the first approach we are using flow case theory, and the system that we are studying is a system with time varying coefficients, whereas here in the next approach we get the steady state as fixed points of certain simplified set of differential equations, and we investigate the stability of the solution by studying the stability of the fixed points. Now, see, this gives you a kind of a brief overview of what are the qualitative features that you could expect in a typical nonlinear system. This is just a tip of an iceberg, there are many more complicating issues, but given that you have an understanding of linear system behavior, this is a list of items that you should start thinking about. Now, why nonlinear analysis is important? There are many reasons. Although many engineering systems are designed to behave linearly, one might think that nonlinearity is not that important in engineering design, but that is not factually correct. For example, in earthquake engineering, we design the structures to be to display controlled inelastic response. There are certain preferred modes of failures and certain failure modes that are not preferred. That means we design the structure to fail in a particular mode. For example, we want to have strong columns and weak beams. That means if a multi-story building is going to fail under an earthquake, the failure should begin with failure of beams, that is slabs and things like that, and not, for example, the ground floor column. If a ground floor column fails, no matter how strong the structure is, the whole structure will collapse. Then similarly, for industrial structures like piping systems and things like that, we use certain supporting devices known as snubbers and nonlinear energy dissipation devices and things like that. These again impart nonlinearity to the system. For example, a heat exchanger pipe in a nuclear reactor conveys fluid at hot temperature. So, in the normal course of its operation, it should be able to withstand the thermal loads because of the conveyance of hot fluids, but in the event of an earthquake, there will be additional support motions. To cope up with thermal loads, the structure needs to be flexible, but that very flexibility brings the natural frequency of the system into the range of earthquake excitation frequencies. So, supports like snubbers in the event of an earthquake they lock the structure and reduce the spans of the piping and increase the natural frequency, so that it attracts lesser seismic loads. Similarly, in wind engineering the interaction between structures and the flow past vibrating structures induces highly nonlinear forcing functions, that I will just briefly mention in the next one of the next slides. Materials like concrete and soil, which are important in civil engineering application, display nonlinear behavior even at low strains. So, the response need not be very large before nonlinearity is switched on. Also they display differing behavior in tension and compression. Then response depends upon entire time history, duration over which the load is applied, and ambient effects such as temperature. Next, if a structure is cracked and it starts vibrating, the closing and opening of cracks induces certain type of nonlinearities that we have to think of. And if you as structure engineers, we are always interested in study of failures, because we want to design structures to prevent failures. So, to understand failures we have to enter nonlinear regimes of responses. A linear system in principle can never fail, it can withstand infinite stresses. There could be problems of loss of stability, this we have discussed, like buckling and snap through and so on and so forth. In many modern application, prototype testing using nonlinear FE models have become popular. For example, crash analysis in automotive design, simulation of draft test in electronic industry, etc. Instead of performing costly experimental studies, cheaper finite element simulations are being used. The sources of nonlinearity in structural mechanics problems can originate from nonlinear strain displacement relations. This type of nonlinearity is called geometric nonlinearity, or the constitutive relations typically relating stress and strain, it could be temperature as well, could be nonlinear. Then nonlinearity associated with boundary conditions, as in contact related problems and so on and so forth, and similarly nonlinear energy dissipation mechanisms. These are some sources of nonlinearity. So, a structure can behave in different ways. For example, the material of the structure could be nonlinear, but there could be small displacements. So, the typical force response diagram may look like this. So, the deformations are not large, but the material of the structure has already entered a nonlinear regime. So, it is nonlinearity in constitutive relations. In the other type of behavior, material may be linear or nonlinear, but large rotations will occur and there are small deformations. So, there are small strains, but large rotations. Now, of course, one can have large rotations as well as large strains. So, these are the most difficult problems to deal with. There could be special conditions, like for example, the same structure is supported through a gap and a loaded spring like this. So, till the time this gap is negotiated, the spring will not come into action, and moment that happens there will be a bilinear nonlinearity, and this type of boundary conditions create what are known as nonlinear boundary conditions. If you write the equation of motion for a simple case again, say mx double dot plus cx plus a nonlinear term, the function g is a function of instantaneous value of displacement and velocity. This is inelastic, this is nonlinearly elastic system. That means upon unloading this force would go to 0, and there will not be any residual displacement. The loading and unloading path will be tracing each other. On the other hand, there could be forces of nonlinear forces which are dependent on entire history of the response up to the current time. So, this typically originates from material nonlinearity, and this originates from geometric nonlinearity. So, a typical force displacement graph for a system exhibiting so called hereditary nonlinear behavior or hysteretic nonlinear behavior is shown here. So, this is something like a force and a displacement, and for a given value of displacement you can see that there are multiple forces possible. Which one will be realized depends on how you have reached that point. That means it depends on the history of the response up to that time. So, this type of systems are more difficult to analyze, as you could expect, than this model. These are difficult to model as well as more difficult to analyze. Now, there are nonlinear effects in, I mentioned about wind engineering problems. So, if you imagine that there is a chimney which is subjected to say flow, this is planar view, the chimney is something like this and the flow is taking place like this. The flow past this chimney will create a pressure field on the object, and if you integrate the pressure field over the surface area, you get a force which can be resolved in line and across the flow directions. And we can show that for certain flow velocities and certain geometries, there will be vortices that will be shed, and because of that there will be dynamic excitations, predominantly harmonic on these chimneys, and these are known as across wind oscillations. So, and if the chimney is flexible, the nature of these excitations become fairly complicated. So, flow past a flexible object can create severe interaction, fluid structure interaction, and for that type of systems there will be a special type of nonlinearity as shown here. I discussed this when we discussed limit cycle oscillations in one of the earlier lectures. You can see here that for small x dot, the term inside the parenthesis will be less than 1, and the net effect of this term will be negative. It is like a negatively damped system, and small oscillations tend to grow. For large amplitude oscillations, the term here becomes negative and induces a positive sign on this, and large amplitudes tend to decay. So, in free vibration, the system displays what is known as the limit cycle behavior. So, and that is a periodic solution, it is an isolated periodic solution, and when such systems are driven by external excitations, there can be complex interactions between the periodic solutions, which are highly nonlinear periodic solutions in free vibration, and the components due to external excitation, and there are very many complex behavior, for one something known as entrainment and things like that. These are again characterized as nonlinear resonances, and if you want to understand the peak response in such systems, you have to understand the basic entrainment phenomena. Now, so with this brief background, we will come to the objectives of the discussion on nonlinear systems. So, the idea here is, the subject is very vast, it cannot be covered in few lectures that I am planning to dedicate to this topic. The idea here is to provide a brief review of background concepts and present a flavor of treatment of nonlinear structural mechanics problems using finite element method. The focus is on geometrically nonlinear problems. We will not be talking about material nonlinearity. By and large, we will be focusing on geometrically nonlinear problems. We can begin with whatever background we have without asking too many newer questions. For example, if you are talking about a planar Euler-Bernoulli beam, if we assume that there are large transverse displacement but small strains and there are moderate rotations, then the changes in geometry due to deformation need not be accounted for while defining stress. So, the point here is, if a structure undergoes large amplitude oscillations, the geometry of the structure also would change. So, that needs to be taken into account while defining stress. So, that modifies many of the basic formulations that we will use for analyzing this system. But suppose we do not get into that, under these conditions probably one can overlook those complications, then we will be able to proceed with whatever background we have. For example, if we assume invoke the Euler-Bernoulli hypothesis that upon deformation the line segment Mn remains straight and normal to the neutral axis and its length does not change, we get the displacement field. This we have discussed a few times, where u1, u2, u3 are displacement along x, y, z respectively, and u naught of x and w naught of x are the displacement of the point on neutral axis. The strain displacement relations that we will be using are nonlinear. We are not using the infinitesimal definition of the strain, we are including the nonlinear terms as well. This I have discussed, the definitions I have discussed in one of the previous lectures. So, the nonlinear strain displacement relations are again displayed here. The quantities that appear in the red are the nonlinear terms. So, for this assumed displacement field, I get epsilon 1 1, I will retain the first term dou u1 by dou x1, but this quadratic term we are not including because we assume strains are small, but dou u3 by dou x1 is a rotation that is included. So, I get this term for epsilon 1 1, that means dou u1 by dou x1 whole square is ignored, but dou u3 by dou x1 is retained. Now, only this strain will be non-zero, all other strains will be 0, and stress again I assume isotropic elastic material. So, stress is related to strain through this relation. I will be able to write the expression for strain energy and the kinetic energy using the assumed form of displacement and the consequent strains, and I get strain energy in this form, and if I now use the assumed displacement form, I get this. You see now there are quartic terms in displacement in the expression for strain energy. So, the terms appearing in red are the newer terms. Now, if we assume the beam to possess symmetric cross section, the terms appearing in red are not the I mean it does not connote nonlinear terms, but the terms which will go to 0 if you assume beam section to be symmetric. So, if that happens, these two terms will go to 0 and I am left with u, which is this, and the second set of terms are the new terms due to presence of nonlinearity. Kinetic energy is given by this. I can write the Lagrangian, and again I will take a 2 noded element with 3 degrees of freedom per node, and we will again interpolate the axial displacement using linear interpolation functions and transverse displacement using Hermite polynomials. I get this set of equations, and if I run through the Lagrange equation, I will get the required equations of motion. So, if you examine the Lagrangian, the first few terms were already encountered when you do the linear analysis. So, they lead to typical mass and stiffness matrices that we have already derived, and the newer terms will originate from these two nonlinear terms. So, suppose if we will focus on one of this, suppose the first term 1 by 8 A E dou w by dou x for dx, and substitute for the assumed displacement form, I get this, and when we run the Lagrangian on this, we will get cubic terms here, and this I j m k is a new integral that has to be determined. So, here we will not get matrices, we will get vectors. So, similarly the other term involving the other nonlinear term, which is this, if we do that, again we get newer nonlinear terms which could be quadratic or cubic. So, I again name some of the integrals that appear here through notation k, I, r, s, k, etc. So, the final form of equation of motion at the element level will be m e u e double dot plus k e u e plus vector of quadratic and cubic terms in u of t. Okay. And the multipliers that appear here are properties of the structural system. Okay. So, this is the equation. So, in free vibration this will be 0. Now, energies in different elements can be added. So, Lagrangian can be constructed for the built up structure using the approach that we have used. There is no change in that aspect of our work. So, assembly of element level matrices and vector can be done as before to obtain global equations of motion. Then derivation of external forces and imposition of boundary conditions again follows the earlier developed procedure, there is nothing new there. The resulting equation of motion for the structure after imposing boundary conditions and after computing the external forces will be of this form in this case. So, this G of u is the nonlinear term that is arising in this model, and this will, as we have seen, it will have cubic and quadratic terms in u. Now, we have already discussed how to solve this equation. See, for example, we during earlier lecture number 16, we have developed a operator splitting methods and other methods to tackle these equations. So, that can be used. I am not going to discuss the solution procedures at this juncture again. Similar analysis can be done for Timoshenko beam. This I leave as an exercise. So, this is the assumed displacement field and this will be the strain, and there will be one more strain which is epsilon 1,3, and you will have to use this expression and construct the Lagrangian. Now, you have to include kinetic energy due to translation and the rotation. The rotary inertial effect also has to be included here. So, once you do that, following a similar procedure, you will be able to derive the equation for Timoshenko beam. Now, this is all right, but how about a more general theory? Now, in a more general theory, we need to allow for measures of strain and stresses to be defined consistent with the deformations, and also we need to allow for material nonlinearity. This we will not be doing, but this we will discuss now. As a structure undergoes large deformation, the cross sectional properties might change. So, when we define stress, we will have questions on some kind of a force divided by an area. Which area are you talking about? Is it the structure in its undeformed configuration or in the deformed configuration? If you say the area is to be computed based on deformed configuration, when you are defining stress you would not know what the deformed configuration is, right. So, and then similarly when you define strains, you have to think about large rotations. I will show either during this lecture or the next lecture that if you use the infinitesimal definition for strains, a structure undergoing rigid rotation, the strains will not be 0. So, that is not acceptable. So, say you can't stick with infinitesimal strain definition, that also needs to be modified. So, some of these issues need to be addressed, and to do all this systematically we need to get into the subject of continuum mechanics and develop all the language and the notations in a systematic way before we can address a simple class of problems. This subject is very vast, as I already said. We are not going to discuss many aspects of this, will not be discussed. I have given a list of references which cover this subject in good detail, and I will be using some of these references during the lecture. Now, the subject of nonlinear analysis of structures is mathematically a lot more refined than a linear analysis. There are many issues associated with notations and as I already said, definition of stress, strain and the balance laws, all of them we need to revisit. So, there are issues about notations. There are 4 sets of notations that one has to use, one has to understand literature on this subject. The indicial notations, I will quickly review this. A set of variables x1 to x1, x2, xn is simply denoted as xi. That means, the indicial here in the name refers to the index to the variables that we assign. The range of values taken by the index I needs to be specified. Typically I runs from 1 to 3 if they are in a Cartesian space, but it need not be so. Now, repeated indices imply summation. For example, if I have a term like alpha equal to I equal to 1 to n ai xi, this is simply written as alpha ai xi, and I have to specify what range it has to be used. I is 1 to n. See, this I is a dummy index. Instead of writing ai xi as well, I can write as xs. So, that I or s is not very important, it is a dummy index. Similarly, a term like this is written as half kij ui oj. You can see that I and j are repeated, therefore, a summation on I and j are implied from I equal to 1 to n. This Kronecker delta is a symbol that is used, delta ij is 1 if I equal to j, otherwise it is 0. So, using that, for example, the length of an infinitesimal element ds square which is given by dx1 square plus dx2 square plus dx square is written as delta ij dxi dxj. There is a symbol known as permutation symbol epsilon ijk. It is defined as shown here. So, you can keep this figure in mind. If you run from 1 2 3 or 2 3 1 or 3 1 2, epsilon ijk is 1. On the other hand, you run in the other way 1 3 2 3 2 1 or 2 1 3, it is minus 1. For all other combinations it is 0. Now, if A is a 3 by 3 matrix, the determinant of A can be written using the permutation symbol in this way. There is a small exercise, there is an identity known as epsilon delta identity. You can show that epsilon ijk and Kronecker delta are related through this identity. Now, there is a symbol for differentiation. Suppose if you consider a function which is f of x1 x2 up to xn, and if df is what I am looking at, it is given by this. This is written compactly as df equal to dou f by dou xi into dxi. The index I repeats and it has to be summed over 1 to n. And this comma symbol, that is a differentiation symbol. If I again have this function f1, f2, f3 to be functions of x1, x2, x3, if I write f of I comma j, it is dou fi by dou xj. Similarly, sigma ij comma k is delta of sigma ij by dou xk. This comma k means you have to differentiate with respect to the kth variable. So, this is like a mathematical shorthand for writing the long expressions. Physics will get buried inside these notations. So, it is not very convenient if you are understanding the subject for the first time, but it is very useful in compactly expressing the results. The algebraic notations, suppose I have a vector with components x1, x2, x3 and y, y1, y2, y3, x dot y is x1, y1 plus x2, y2 plus x3, y3, and x cross y is given by this, and this is written as zi is epsilon ijk xj yk. Then grad, that is this this delta inverted delta is this operation E1 dou by dou x1 plus E2 dou by dou x2 plus this, it is written Ei dou xi. Now, this is a scalar function. If you take a grad of a scalar function, it is given by dou f by dou xi, that means ith component is this. Now, if you apply the grad operation on a vector valued function f, we can define what is our divergence, which is del dot f, which is given by this. This is a dot symbol. The curl is delta cross f, and that is given by this. Now, if you apply a grad function on a vector valued function, it is written on delta comma f, this is given by this, and f itself is a vector, therefore, I have to write this. So, you can see that grad of a vector valued function will have these gradients present in their representation. In matrix notations, we arrange the components of a vector in a column like this, and even stress is arranged as a column like this, right. So, stress is a tensor represented a 3 by 3 matrix, but in this so called white notations we write it as 6 cross 1 vector. Similarly, strain. So, the strain energy is written as half sigma transpose epsilon. So, we represent the terms like this, for example, r square is written as x transpose x and so on and so forth. So, when doing this we do not write explicitly the connective symbols. For example, when I say x transpose x, I am not putting in between any dot or a multiplication or any other symbol. In tensor notations, indices are not shown. This is applicable to Cartesian and other coordinate systems. xi, yi, that means it is summation of is x1 y1 plus x2 y2 plus x3 is simply written x dot y. Aij, bij is written as a double dot b. This is a new symbol that we will use. Colon denotes contraction of pair of repeated indices, whereas a dot denotes, a single dot denotes contraction of inner indices, whereas this double dot denotes contraction of pair of repeated indices. So, this relation sigma ij, Cij, Kl, epsilon Kl is in tensor notation is written as C double dot epsilon. So, I have given some examples of writing different expressions in alternative notations, this you can examine. So, if we have something like phi transpose k phi, in tensor notation it is written as phi dot k dot phi, in indicial it is phi I, k I j, phi j. Similarly, you have half epsilon transpose C epsilon, this is written as half epsilon double dot C double dot epsilon, whereas this epsilon I, C I j, epsilon j. So, so on and so forth. This and the equilibrium equations for elasticity is in the longhand in full notation form, it is given by this, in matrix form it is given by this, in indicial it is given by this. Actually, the full notation is a notation of last resort, where everything is spelled out without cutting down any you write all the terms, and this clearly becomes cumbersome if you have to deal with this type of equations too often. Now, I will start now a quick review of continuum mechanics. There is what is known as continuum hypothesis. So, according to this hypothesis, material is infinitely divisible and each infinitesimal element retains all the properties of the material. So, that Newtonian mechanics is directly applicable, that means calculus works, that means concept of elementary strip and things like that work, and we can derive the governing physical laws can be expressed as partial differential equations or as ordinary differential equations or through variational arguments. Now, obviously we know matter is not infinitely divisible, it breaks down to elementary particles if we do that, but that we are ignoring in this hypothesis. So, consequently we need to focus our attention to characteristic dimensions, which is about greater than about 10 to the power of minus 6 centimeter. So, if you are dealing with dimensions less than this, then continuum hypothesis needs to be I mean you have to look at other possible effects that are present in the physics of the problem. Just to give in this context, diameter of a water molecule is about 10 to the power of minus 8 centimeter. So, if you are dealing with fluid mechanics problem in which the medium is water, the fluid is water, then you cannot think of sizes less than 10 to the power of minus 6, characteristic lengths less than this. The continuum mechanics theory is valid for both solids and fluids, it does not distinguish between the two, and due to the assumption of existence of continuum, notions of density, temperature, pressure at a point make sense. The primary aim is to model macroscopic behavior of solids and fluids. So, just to emphasize again, it ignores the atomic structure of the matter, and also matter consists of discrete particles which are perpetually in motion, even this motion is not included in our analysis. Then questions on treatment of molecular, grain or crystal structure are not addressed in continuum mechanics. There are different themes in continuum mechanics. We talk about kinematics, where we talk about motion and deformation, kinetics where we talk about concept of stress, and there are different balance laws which basically enunciate certain physical laws. I will come to some of them which are common to both fluids and solids. In the context of nonlinear structural mechanics problem, what is crucial to gain a reasonable understanding of the subject is to understand how rotations are dealt with. Rotations are very crucial in problems of nonlinear analysis, and what is the need for defining alternatively, what is the need for alternative definitions for stresses and strains, and then how to treat material nonlinear behavior. So, we will start some simple questions about kinematics. Kinematics is study of motion and deformation without concerning with causes of motion and deformation. We do not talk about forces which create the motion and deformation, we simply focus on geometry. So, here we talk about a reference configuration, say let us assume body B at time 0. This omega naught is a domain, gamma naught is a boundary, and we consider a Cartesian coordinate system. So, capital x1, x2, x3 is for body at time t equal to 0. Now, during the process of deformation, every point here with position vector OP, which is x, gets mapped to another point P whose position vector is x. This x is related to capital X through this relation. So, this is a mapping of the deformation. The reference frame, the origin is at 0 and there is a orthonormal basis E1, E2, E3, this is a coordinate system. The body B occupies different regions omega naught, omega 1 etc., omega at times t equal to 0, 1, 2, T1, T2, T3 and T. The regions omega naught, omega 1 etc., omega occupied the body at different time instants are known as configurations of the body at the respective time instants. At time t equal to 0, we say that omega naught is the initial state of the body or the initial configuration. It could also be taken as reference configuration with respect to which motion is described. There are other names like it is taken to be undeformed configuration. It is an idealization, nobody is truly undeformed because the gravity and things like that always act on them. So, what you see as a reference configuration is already deformed due to one or the other effects. Now, gamma naught is a boundary of the initial configuration. At time t, this is the current state of the body, the current deformed configuration. Gamma is the boundary of the current configuration. So, this is gamma 1. There are two coordinate systems that we can think of using to describe the problem. One is known as Eulerian, the other one is Lagrangian. In Lagrangian description, we take x1, capital X1, x2, x3 comma t as independent variables. That means the point P is described by its position in the initial configuration, that is capital X1, x2, x3. Those x1, x2, x3 are taken as independent variables. In Eulerian description, we take the lowercase x1, x2, x3 as independent variables. Now, x is written, position vector x is written as xi ei, which is nothing but x1 e1 plus x2 e2 plus x3 e3. So, this is a position vector of a material point in the initial configuration. This does not change with time, because initial configuration is some reference position that does not change with time. it labels all material points, whereas x, the lowercase x, which is again xi ei, this provides the position of a point in the current configuration, changes as configurations evolve in time. In problems of solid mechanics, we adopt Lagrangian descriptions. The Lagrangian description is also known as material description, and the Eulerian description is also known as spatial description. The motion itself, that is this function phi of x t, is defined motion, that is a coordinate in the current configuration, a point in the current configuration, that is the position vector of a point in the current configuration is related to where the point was in the reference configuration through this function. So, this is in longhand, it is there are 3 functions x1, x2, x3, phi 1, phi 2, phi 3 that relate the capital x1, x2, x3 to the lowercase x1 and x2 and x3. When reference and initial configurations coincide at t equal to 0, x of x comma 0 is capital X. So, that would mean which is phi of x comma 0. So, then xi of xi x comma 0, this is the definition, which is phi I of x comma 0, and this is an identity transformation. So, in material coordinates, displacement is given by x minus capital X, which is nothing but phi of x comma t minus phi of x comma 0 or phi of x comma t minus capital X. Velocity is its time gradient, capital X does not change with time, therefore, the gradient is simply du by dt as shown here. There is no dou u by dou x term which gets multiplied by dou x by dou t, that is not there because capital dou of capital X by dou t is 0. So, similarly acceleration also can be defined. On the other hand, in the spatial coordinates, if you want to define the gradient of a vector, say function say phi of x comma t, this is dou phi by dou t plus dou phi by dou xj and dxj by dt. So, this is there will be a new term. So, acceleration gets defined like this, and this is the definition of acceleration if you are looking at spatial coordinates. Now, a primary quantity of interest in discussing deformation is what is known as deformation gradient. So, the problem is the question is, the issue is this is the configuration of the body at time t equal to 0 and PQ is a line segment. Upon deformation, capital P goes to small p and capital Q goes to capital Q, and this line segment dx gets mapped to this lowercase dx. The question is how this dx is related to this capital Dx, and that will be through a matrix known as deformation gradient. So, we will take up this discussion on deformation gradient and follow up this topic in the next lecture. So, we will close this lecture at this point.